Dear students, I'm gonna start again with the portion on linear springs. And then we'll move on from there. So consider of stiffness K and unstretched length L0. Okay. So a spring of stiffness K and unstretched length L0 attached to a mass M. Okay, so take the origin to be at M when the spring is unstretched. Okay, so we're gonna take the origin, so this is the spring. Considering three cases. The spring is unstretched, stretched, and compressed. So stretched meaning extended. So here, let us define L to be the current length of the spring. Then here, L is equal to L0. Here, L is greater than L0, and here L is less than L0. So if we calculate S, which is L minus L0, which is the stretch of the spring, here S is negative, S is positive, and S is equal to 0. The stretch is the difference between L and L0. So L minus L0 is the stretch, and in this case, let me fix my notation a little bit. This is my S here, and this is my S here. So in the extended case, S is positive, and the compressed case, S is negative. So if I express the force, Fs is equal to minus Ks Ex, where this is Ex, and this is Ey, then in the extended case, S is positive and Fs points along minus Ex, like this, which makes sense. The box is gonna have a force that points like this, that is gonna seek to return the spring to its original length. So S is negative, so the spring force points like this. Again, it seeks to return the spring to its unstretched case. Okay, And in this particular problem, because we took our origin to be at the location when the spring is unstretched. So if I take my origin to be here, then the stretch is equal to just x. My position vector, remember, goes from the origin to the particle. So here, r is x ex, and this is equal to s ex. But that's only true in this particular case. Because we can consider another case, for example, well, before we consider another case, let me give you the general expression for the spring force. If I have in general a spring fixed on one end and attached to a mass m on the other end, let me call this part where it's fixed A and then mass m, and I have an origin, any location. Ra is the position vector from O to the origin, and r is the position vector from O to the particle. And I can write also the vector r minus Ra. It's gonna be this vector, r minus Ra. So the spring force is directed along r minus Ra, but I'll add a minus sign. We're gonna see why. And it's proportional to the stretch. So K is the constant of proportionality, the spring constant, and S is the stretch. So S is L minus L0, current length minus initial length, and L is just the magnitude of R minus Ra. Okay, and when when the magnitude R minus Ra is greater than L0, the spring is extended. And then Fs points along minus R minus Ra. So the spring is extended like this, and the spring force points like this, which makes sense. And this equation is also valid if the spring is extended. Less than L0. Fs points along minus R minus Ra, because this is the stretch is negative and then the minus sign cancel out. So the spring force points like this, which makes sense. So this equation is valid, and that's a good time to stop and actually think about it. And you can think about it in this simple case, that these directions or this expression holds both when the spring is extended and compressed. So then this expression holds when the spring is extended or compressed. Really, it holds in any configuration, even in 3D. So let me highlight this equation. Okay, and we can use that to solve problems. So if I go back to the simple case of this spring, with mass m, this is rectilinear motion, R is x ex. So this is continuing the example we started this video with. V is x dot ex, A is x double dot ex. Let us draw the free body diagram. We have the weight, the normal force, and the spring force. weight minus mg ey. The normal force is is n ey. So this is n, this is ex, and this is ey. Okay, and I still have the spring force. So we know that it's gonna be from here minus kx ex from this equation here. Let me just start with the so just for educational purposes, for understanding, let us start with the general expression. Okay, so the general expression is Fs is equal to minus k, or sorry, let me put the k inside the parentheses, minus k r minus ra minus L0 times r minus ra with a minus sign here. Okay, perfecto. So let us figure out what r and ra are. So in general, if I have the mass, and usually I would advise you to, when you're considering a general case, to consider a case when the spring is extended, so that you don't have to worry about a lot of minuses. Okay, so the origin is here when this length is L0. And this is A, the fixed end of the spring, and then this is the position vector from the origin to the particle. I can also draw RA, the position vector from the origin to A. So RA is always going to be fixed because the origin is fixed and A is fixed. So RA is minus L0 EX. That's, again, EX and EY. And R is X EX, based on our previous discussion, which is basically L minus L0, the stretch, EX. So then I can write that R minus RA is L minus L0 EX minus L0 EX, which is L EX. So R minus RA over the magnitude of R minus RA is L EX over the absolute value of L, but L is always going to be positive because the current length of the spring cannot be negative. So that's EX. So then I can write the spring force Fs as K, the magnitude of R minus RA minus L0, which is L minus L0, which is S, which is X in this case, and then minus EX, minus K X EX. Okay. So that's the spring force in this case. So then going back to our original problem, if we want to write the balance of linear momentum of the body, we will do F equals ma, and we will write minus mg ey plus ney minus kx ex is equal to m x double dot ex, and I can take projections along ex, for example, to find that the mx double dot plus kx is equal to 0. This is the well-known equation of motion for a simple undamped oscillator. Okay, so let me review what we did in this video, and in the next video we'll do an example. So we started with kind of motivating the Hooke's law, the spring force that acts on a spring, and we took a simple example in one dimensions where the spring is going, the spring and the mass are going in rectilinear motion, and we derived this equation in green here, and it applies when the spring is both stretched and unstretched. In general, we have this equation also in green that applies in all cases when the spring is stretched or unstretched. S is the stretch of the spring, which is the current length L minus the unstretched length L0. R is the position vector from the origin to the mass, and RA is the position vector from the origin to the fixed end of the spring. I'll see you in the next video for an example.